Okay, everybody, we're going to start 4.4 today, Lhopitals Rule. So Lhopitals Rule is basically a way that we can deal with some of the limits that either required a whole bunch of effort using algebra or other forms of simplifying, or that just simply we could not do. So it's kind of our secret weapon against limits, okay? So L'Hopital's rule helps us deal with certain limits where simplifying and algebra are not enough. In the past problems, we have encountered 0 over 0 or infinity over infinity. These are basically the general indeterminate forms. The limit may or may not exist when this occurs. You're not quite sure what it is. Some people believe it will equal 1. That is not always the case. It may happen every once in a while, but in general, this is not usually the case. Below are some examples of these forms where we are able to work through the problems. So we have done problems where we ran into this. So if we were doing this first one here, it says the limit as x approaches infinity, we would have x plus 1 over the square root of x. If we were to try to let x approach infinity, we end up with infinity over infinity. So we would end up with this form, infinity over infinity. And in this case, we know that we could have done algebra and split it. So we could have just done this, right? We could have split it like that. And we would have, let's see, x divided by the square root of x is x to the 1/2 plus 1 over x to the 1/2, okay? Now, if you take the limit piece by piece, you know that this limit will become 0, and then the other one will become infinity. So in this particular problem, we end up with infinity over infinity ends up becoming infinity, definitely not 1. Let's take a look at this other problem. If we plug 0 into here, well, 1 divided by something infinitely close to 0 would become infinitely large. So the form we're going to end up with is 0 divided by, oops, I'm sorry, not 0 divided by 0. Infinity divided by infinity. If we put 0 into both of those denominators, we know we can't actually plug 0 in, but we can get so close to 0. That's what the limit allows us to do. However, you guys know that you could have just rewritten it as x approaches 0, 1 over x squared times the reciprocal of that, which would be x to the 4th over 1, which would become the limit as x approaches 0 of x squared, which in this case would become 0. Okay, so these are both cases where we end up with infinity over infinity and we don't get 1. One time we get infinity, one time we get 0, another time we may get like 7 or e or whatever the case may be. Okay, now here's an example that if we plug 3 in, we get 3 minus 3, which would be 0, and we get 9 minus 9, which would be 0. So this would be the form we would get, which we know is indeterminate, meaning the limit may or may not exist. So you guys have done in the past, limit as x approaches 3 of x minus 3 over x minus 3, x plus 3. So we use factoring this time. We use some of our algebra. We can cancel x minus 3 and x minus 3, and our limit will end up being 1 over 6. So in this case, 0 over 0 ended up becoming 1 over 6. Okay, so these are all problems that we could use algebra to simplify, but that will not always be the case. Sometimes you just can't do anything. So that's where L'Hopital's kind of steps in. So L'Hopital's rule says, suppose f of x and g of x are differentiable, and g prime of x does not equal 0 on some open interval I that contains a, except possibly a itself, okay, except possibly at a. Suppose further that the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to 0. Or the limit is of f of x as x approaches a is equal to plus or minus infinity, and likewise the limit as x approaches a of g of x equals plus or minus infinity. So this means that if you take the limit of these two things, you're going to say the limit of f of x over g of x as x approaches a would end up becoming 0 over 0 or infinity over infinity. Okay, so you're saying you're going to run into these two indeterminate forms, right? That's what you're saying. You're going to run into these two indeterminate forms while we're working with this. Okay. All right. So So these are kind of our general base indeterminate forms that we need to use, that we always are trying to work with, okay? Well, what Lhopitals rule says is if you ever run into this, 0 over 0 or infinity over infinity, then you can say that the limit as x approaches a, so this limit as x approaches a of g of x, I'm sorry, of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, okay? So if the limit on the right exists or equals to plus or minus infinity. So what we're saying is that the limit as x approaches a of a quotient of f of x and g of x is the same as the limit as x approaches a of the quotient of their derivatives separately. So you're not doing the actual quotient rule. You are literally taking the derivative of the numerator and the derivative of the denominator as two separate entities. So let's see how that works, okay? So let's take a look at this problem. We have the limit as x approaches infinity of x squared ln of x, all right? So here's the thing. You first must always check that you're gonna get our indeterminate form of 0 over 0 or infinity over infinity. If you don't check that, you may end up using Lhopitals rule when you're not supposed to, okay? So Lhopitals rule only works with these cases, okay? So we're gonna try to take a look at this, and we see that this would end up becoming, if I plug infinity in, I get infinity over infinity. So this would be the form, right? We're gonna end up with this form. Now we can't say it's equal to it because we don't know what infinity over infinity is worth. So we're gonna say that we're gonna end up with this indeterminate form. So this means Lhopitals applies, right? So you don't have to write this, but in your mind, you're thinking, well, this means Lhopitals applies, okay? So what I'm gonna do is I'm then gonna take the limit as x approaches infinity, okay, of x squared over ln of x. And I'm going to do this little writing right here. This is how I like to do it. I write a little equal sign with a LH, meaning I'm applying Lhopitals rule. And that means that I'm going to do the limit as x approaches infinity. And now I'm going to take the derivative of x squared, which is 2x. And I'm going to take the derivative of ln of x, which is 1 over x. Now I'm going to clean this up. So this will become 2x times x, which will become the limit as x approaches infinity of 2x squared, which you guys know is infinity, in fact, okay? So in this case, infinity over infinity became infinity, okay? So the limit as x approaches infinity of x squared over the ln of x is actually worth infinity, okay? So this is how you can use Lhopitals. And notice I did not do the quotient rule. We're not doing the quotient rule on x squared and ln of x. We're taking the derivative of each of them as separate entities, as separate problems, okay? So that's our first example of Lhopitals, okay? So let's take another one. Let's look at a trig example. So let's find the limit as x approaches, let's say 0. X approaches 0 of sine of x over x. Now we've done this problem before. We know that the answer is 1. This is one of the limits I asked you guys to memorize. But now we can use Lhopitals as a faster way to justify it. So first things first, does Lhopitals rule apply? Well, if I plug 0 in, the sine of 0 is 0 divided by 0. So we would end up with 0 over 0, right? So we have the form we need. So all I'm going to do is I'm going to do the limit as x approaches 0 of sine of x over x, and I'm going to put a little equal sign with an LH there to symbolize that I'm about to do Lhopitals rule. So now we have the limit as x approaches 0. The derivative of sine x is cosine x divided by the derivative of x is 1. Now when we plug 0 in, we just get 1. And that's how Lhopitals rule can help us with problems that were difficult in the past. Now this one you happen to memorize, but proving why this was the case is a different matter altogether. So now we can use Lhopitals just to say, hey, look, we can do this problem and set it equal to 1. All right, now let's look at another example. Let's do something with an exponential function. Find x approaches, let's do infinity of e to the x over x squared. Okay, so now we notice that this would be infinity over infinity. So we're going to go and we're going to say, okay, well then L'Hopital's applies. So I'm going to do, and you could even jump to it now and start skipping a few steps. You could say, well, let's do L'Hopital's. And we know the limit as x approaches infinity of e to the x, the derivative of e to the x is e to the x, and the derivative of x squared is 2x. But here's the problem. This is still infinity over infinity. So what I'm going to do is I'm going to do another L'Hopital's, because I still ended up with infinity over infinity, so I should still be able to apply L'Hopital's. So then this derivative is e to the x, and this derivative is just 2. Now we get infinity as our answer. So we're able to kind of speed things up because we're getting more comfortable with L'Hopital's rule. Okay. Now let's look at it. So you guys can apply L'Hopital's rule as many times as possible. So now think about it. What if the denominator was x cubed? Then that means we would have needed to apply L'Hopital's rule 3 times instead of 2. So sometimes you can kind of see it when you notice it. But L'Hopital's, like I said, is kind of doing a lot of the grunt work that we had to do with algebra before, or maybe we couldn't even do it. Now we are able to use L'Hopital's. So a lot of the problems from our first exam with limits could have been beaten by L'Hopital's, okay? So let's look at example 4. It says, find the limit e approaches 0 of 1 minus e to the 3t plus 3t all divided by t squared. Okay. Now here's the thing. Let's see here. Well, if I plug 0 into 3t, we get e to the 0 plus 0. So e to the 0, we know that this is going to become 1. We know this is going to become 0. So this will become 1 minus 1, which is 0. So we're going to end up with 0 over 0. Okay, so that means L'Hopital's applies. So we're going to keep moving. We're going to say, well, this means that I can take the derivative of the numerator and the denominator separately. And the derivative of 1 is 0 minus e to the 3t. So this would be minus 3 e to the 3t. Remember, using our chain rule on e, plus 3 all over 2t. Now the problem with this is if we look at this again, we're going to notice that if I plug 0 in right here, that's going to become e to the 0, which will be 1, times negative 3. So this would become 0 over, or negative 3 plus 3 is 0, divided by 2 times 0. So I still get 0 over 0. So I'm just going to do L'Hopital's again. And this is going to be the limit as t approaches. And make sure you guys are continuing to write the limit until you actually use the limit. Okay, so the limit as t approaches 0 of negative 3 times 3 e to the 3t. The derivative of 3 is 0 over 2. So this now will become what? Negative 9 over 2. That's our answer. All right, so hopefully you guys are kind of getting the hang of L'Hopital's now. Okay, let's see if I got another one. Yeah, let's try this one. So let's try example 4, or this is example 5, I guess. Okay, so it says find, let's use a left-handed limit. So find the limit as x approaches pi. Let's go from the left of sine x over 1 minus cosine. Okay. So some of you might jump right into L'Hopital's, and you might say, oh, well, L'Hopital says that we have the limit as x approaches pi from the left, and the derivative of sine is cosine x over the derivative of cosine is negative sine. So this would become plus sine because there's already a negative there. And then this is actually, you plug in pi into, from the left-hand side, this is technically cotangent. So I believe you would get, if you look at it graphically, I believe you would get negative infinity, okay? However, what are we doing? We never check to see if Lhopitals apply, so we should not be doing this. This should not be happening. We gotta check first. Well, wait a minute. What if I plug in pi from the left? Well, sine of pi would be 0, right? The sine of pi would be 0, and this becomes 1 minus, what's the cosine of pi? Well, the cosine of pi is negative 1, so this becomes 0 over 2, which is 0. Well, that's a fine limit. There's no indeterminate form. There's nothing wrong with that. So you guys are able to, just plug the limit in and go from there. So remember that not everything is applicable, or not everything can be used with Lhopitals rule. Okay, so you can, and notice this one gave us the wrong answer. It gave us pi. This is incorrect, or negative infinity. This is incorrect. The correct answer was actually 0. So remember, when you're doing problems that ask you for limits, you have to check first if Lhopitals applies. And if it doesn't, then you cannot use it. Or you might have to do work to make it become applicable. Okay? So let's take a look at another one. So now we can run into other forms. So let's take a look at some other forms. Okay? So we can have certain limits again. We can have certain limits. We can end up with these forms. And then we can use algebra to clean it up. So we're kind of going to go back and look at what we were doing before. So limit as x approaches infinity of x plus 3 minus, okay? So if you were to do this and not try to clean it up, you would end up with infinity minus infinity. But you know that, and we don't really know what infinity minus infinity is, so we do know that we could have done some cleanup first, and we could have combined like terms, and the x minus x would become 0, so we would just be looking at the limit of 3 as x approaches infinity, and that's just 3, okay? So we could look at another problem. The limit as x approaches infinity of x squared times x. Oops, x squared minus x. Well, once again, this would be infinity minus infinity, okay? But you know that this is actually the limit as x approaches infinity of x times x minus 1, which is really infinity times infinity, which is just infinitely large, okay? Now we can take a look at another one. We can do the limit as x approaches 0 of x times 3 over x. That becomes 0 times infinity, because 3 divided by an infinitely small number is an infinitely large number. So we get 0 times infinity. But we know that this is actually, we could have used cross-canceling, and we would have had x times 3 over x, and we could have just canceled the x's. And this would just become 3, okay? Oops, let me, hold on 1 second. I think I was doing the wrong part. Yeah, okay, no, that's okay. So we know how to do infinity minus infinity or infinity times 0, or 0 times infinity, but what if these nice little simplifications don't work? So let's take a look at, I believe this is example 6. So example 6. Says find the limit as x approaches infinity of x times e to the 1 over x minus 1. Okay, so if we try to plug this in right now, we would get infinity times 0, right? We would get this situation. So infinity times And e to the 1 over infinity would be e to the 0, and e to the 0 is 1, and 1 minus 1 is 0. Well, we don't know exactly what infinity times 0 is going to become. These are two of the most powerful numbers in mathematics. You have something that stands for nothingness, and then you have something that stands for the largest thing there can be, or the concept of that, the largest number. So we're not really sure what the outcome would be, but we know if we could somehow write it as 0 over 0 or infinity over infinity, we could use Lhopitals. So what we're going to do is we're going to do a little bit of algebra to help us get to Lhopitals, okay? So what we're going to do is, let's see here, we're going to factor out, or we're not even going to factor, let me try this. So we're going to say the limit as x approaches infinity of e to the 1 over x minus 1 divided by 1 over x. I'm going to do a little trick with algebra. Now remember, dividing by 1 over x is the same as multiplying by the reciprocal. And what's the reciprocal of 1 over x? Putting this in the denominator makes it the same as that. So we actually haven't done anything to the problem. But now, when I put infinity in, or when I try to let x approach infinity, we're going to end up with this situation. E to the 1 over infinity is e to the 0, so we end up with 1 minus 1 over 1 divided by infinity is 0, so this is 0 over 0, which means Lhopitals rule now applies. So now we can jump to this and we can say equals Lhopitals limit as x approaches infinity. The derivative of e to the 1 over x, remember, that's basically saying this is x to the negative 1. So remember, you have to do e to the u times u prime. So what's the derivative of x to the negative 1? The derivative of x to the negative 1 would be negative x to the negative 2. So this will become negative x to the negative 2 times e to the 1 over x. That's my chain rule on my e, my exponential e to the x function, over or minus 0 divided by, now what's the derivative of 1 over x? It's negative x to the negative 2, right? So I took the derivative of the numerator and the denominator. These will cancel. It'll become 1, right? And now this becomes the limit as x approaches infinity of e to the 1 over x. But e to the 1 over x is okay to use x approaching infinity. This becomes e to the 1 over infinity, which will be e to the 0, which is just 1. Right? Because if you think of this as getting infinitely large, that becomes 1 divided by an infinitely large number, which is approaching 0. E to the 0 is 1. So we were able to find our solution to this limit, and it is in fact 1, all right? So hopefully you guys are pausing the video and trying these on your own to see what you can do. All right, let me see if I got another one for you. Let's take a look at this one. Let's call this example 7. Okay, so example number 7 says, let's try the limit. Okay, that's fine. The limit as theta approaches pi over 2 from the left-hand side of secant theta minus tan theta. Okay, so let's see the form. So if we do secant, secant is 1 over cosine, and the cosine of pi halves from the left-hand side. So the cosine of pi halves from the left-hand side would be what? So if you're not sure, take your unit circle, right? Well, actually, we could maybe do it a little bit better with this. So here is, there's pi, right? There's 2 pi, right? And then we have halves right here, and 3 pi right here, okay? And we know that the cosine function, right? The cosine function starts at 1, right? So the cosine function, let's call this 1, starts here. It's going to go down to 1, right? It's going to come up. Fix this a little bit. Right here at 1, and it's going to come back up. Wow, that's pretty bad. Okay, let me just clean this up. Sorry, that's pretty bad. So that's basically if we do one period of the cosine function. But then we know that everywhere there were x-intercepts, those are going to be asymptotes for the secant function. So that means right here we got this, and right here we got this, right? And then right here we have this. And so the red is actually the secant function. And we want to know what's happening when we get close to pi halves from the left-hand side. So as we're getting closer and closer and closer to pi halves from the left, well, we're getting closer to 0. Okay, right? So here we're getting closer and closer to 0. And then the tangent function at pi halves is also, let's see, pi halves would be sine over cosine, so we're also 0. So we end up with pi halves from the left. Oh, yeah, so here, let me show you guys right here. So think about this. Look right up here. From pi halves from the left, look what we're approaching. What's that height up there? We're approaching a height of positive infinity, right? And then if we're talking about the tangent function, we're also approaching infinity. So we end up with L'Hopital's form of infinity minus infinity, which is, once again, not what we're looking for. But normally when you run into these, it's a kind of a giveaway that you should probably try to clean it up, use some algebra or something to get it into fraction form for L'Hopital's, okay? Because remember, we need 0 over 0 or infinity over infinity, okay? So what we're going to do is we're going to say the limit as theta approaches pi halves from the left. I'm going to rewrite this. I'm going to rewrite secant as 1 over cosine theta. Remember, I haven't done L'Hopital's because I'm not in the right form yet. Minus sine theta over cosine theta. But that's really the limit as theta approaches pi halves from the left of 1 minus sine theta over cosine theta. Right. Now let's try to plug that in. Well, the sine of theta at pi halves is 1, and the cosine of theta at pi halves is 0. So we end up with 1 minus 1, which is 0. And we end up with cosine of theta, which is 0. So we end up with 0 over 0. So remember, this is what we're looking for. We're trying to see if we can get to L'Hopital's form. So now we have the indeterminate form we've been waiting for. So now we can say L'Hopital's applies. And we're going to do the limit as theta approaches pi over 2 from the left. And now I'm going to take the derivative of the numerator. What's the derivative of 1 minus sine theta? Well, that would be negative cosine theta. Divided by the derivative of cosine theta is negative sine theta. So now the derivative of cosine of, I'm sorry, now we can try to plug in our value. Pi halves of cosine would be z, so easy, so, right? So the cosine of pi halves is 0. The sine of pi halves is 1, so we end up with 0. So we found our limit, okay? So hopefully you guys kind of followed along what I did up here. All right, so right up here, you guys kind of followed along. I'm approaching pi halves from the left-hand side, and the height I'm approaching is positive infinity. Remember, that's what the limit is for us sometimes, it's just the height, okay? So that's a little bit harder when using trig. Okay. Let me see, let's look at some other indeterminate forms. So oftentimes these are called exponential indeterminate forms. Okay. So let's just write a few of these out. Form form oops, I got it backwards, I'm sorry guys. So let's say we have the limit as x approaches infinity of 10 to the x, 1 over x. Well, 10 to the x is infinity, and 1 over x is 0. So this is infinity over 0, okay? But in reality, you know that you could have done this. You could have done the limit as x approaches 0 of 10 to the x times 1 over x, because remember, a power to a power, the powers multiply, and this just becomes the limit as x approaches infinity of 10, which is 10. So in this case, we didn't need to do Lhopitals. It actually cleaned up, but it started off in a weird form of infinity to the 0, okay? Another one we can look at is the limit as x approaches infinity of 3 to the x, 1 over x, which we know would be 3 to the infinity, which is infinity, to the 0 again. But we know that x approaches infinity. We could just take this once again, and we would get 3 to the x times 1 over x. And we would get, oops, hold on, I messed up a little bit. Let's go back. If we take, I'm supposed to be doing this limit as x approaches 0. I'm sorry about that, otherwise it would be identical to the previous problem. So this is actually 3 to the 0, which we know is 1, and 1 over 0 is infinitely large. So this is 1 to the infinity, which we would think would just be 1, but in this case, it's actually the limit as x approaches, let me fix this real quick, of 3, which is just 3, so not 0 at all, and not 1. You know, it's actually 3. We have one more form that we could talk about. So we have infinity to the 0, 1 to the infinity, and now we're going to have 0 to the 0. So we're going to take the limit as x approaches 0 of x to the x, okay? And this would become 0 to the 0, okay? So this one is a slight problem. X to the 0, sorry about that. X to the 0 equals 1, but 0 to the x equals 0. So this is definitely a dilemma. We don't really have a fix for this, okay? So these are problems that we're going to have to kind of mess with a little bit. These, I would say, are the hardest problems from Lhopitals. So let's look at example 8. So example 8 says, find the limit as x approaches 0 from the right of x to the 3x. So this is a much harder problem, and if we try to plug 0 in, we end up with what? 0 to the 0. So we would end up with this form 0 to the 0. Okay, so that means that it probably is some kind of it is an exponential indeterminate form. Okay, however, normally when I see these, that to me is a warning, like, hey, this doesn't work, but I bet you there's some manipulation you could do to turn it into Lhopitals form. So that's what we're going to kind of struggle with for this problem, is how can we fix this and make it Lhopitals form, okay? Or the indeterminate form of 0 over 0 or infinity over infinity. So the first thing you need to do is you need to name it. I'm going to name this limit y. So, and it seems like a little thing, but once we've named it, we have more options to us, okay? So now we're saying that y is equal to this limit. And just so you guys know, what's causing the problem is x to the 3x. The 3x in the exponent is causing the problem. So hopefully you guys remember that there was a certain function that allowed us to bring exponents down and put them on the level playing field. So if you remember, natural logs had a property that allowed you to take exponents of the argument and move them to the front of the log and make it multiplication. So we're going to do that right now. We're going to take the natural log of both sides, okay? So this becomes the ln of y, natural log of y, is equal. Now there's a property of limits that says the natural log of the limit is the same as the limit of the natural log. So I'm going to rewrite this as the limit as x approaches 0 from the right of the natural log of x to the 3x, okay? However, we know that that means the ln of y is equal to the limit as x approaches 0 from the right of 3x ln of x. So I was able to move this into the front, not because of derivatives, but simply a property of logarithm, okay? Now the thing is this isn't quite Lhopitals, because if I plug 0 in here, I end up getting 0 times 0 times infinity, I believe. Yeah, 0 times infinity. So this still doesn't quite work because, or actually 0 times negative infinity, I believe. But either way, it's 0 times infinity, which is not good. So we remember a trick we have that said that the ln of y is equal to the limit of 0 from the right. And we were able to rewrite this from a previous problem. Remember, we were able to put the 1 over x on the bottom. And what's the reciprocal of 1 over x? It's x. So this is another way we can do this problem, where we end up now with 3, this would be negative infinity. So it would be negative infinity over infinity. So we would get Lhopitals form. So that means that Lhopitals applies. So now we can do this. We can say ln of y, the natural log of y, is equal, and I'm going to do Lhopitals to the limit as x approaches 0 from the right of 3 over x, right? The derivative of ln of x is 1 over x, and 3 times 1 over x is 3 over x, divided by the derivative of this would be negative 1 over x squared, right? Because this is really just x to the negative 1. So if I took the derivative of that, I would be able to get negative x to the negative 2, which is negative 1 over this. So now I'm going to rewrite this. So I have ln of y equals, well, no, I guess I could just say this equals. So this equals the limit as x approaches 0 from the right. And this would become negative 3x, I believe, once you clean it up. And then that is actually 0. However, nobody ever asked us to find the natural log of y. They wanted to know the limit. So right now, we have ln of y is equal to 0. So we need to rewrite this in exponential form. So this would be e to the 0 is equal to y. So then we know that y equals 1. But what was y? If we go way back up to the beginning, y was this limit. So now we get to say, then the limit as x approaches 0 from the right of x to the 3x is equal to 1. And this is our answer, right? Because e to the 0 is 1, okay? So that's what I would consider one of the harder problems. Definitely something you want to take a look at. There's a few of these in the homework, whether you do it online or in the book. These are definitely the harder ones when you're doing these exponential forms. Form is this is 0 to the 0. So let's see here. Let's try one more. Let me see if I have a better one. You know what? I have a few other ones that I want to save for our in-class meeting. So give these a shot. I'm going to end the video now. This should get you started on everything, but obviously we still have to go over a few of the other forms, and 1 to the infinity is another one I'm going to do. But this should kind of get you through. Thanks for watching, guys, and I'll see you in the next meeting.